Welcome to this lecture on Solution to Exercise 5.3, Question 15 to Question 19 from the book Bartle and Sherbert.
Welcome everyone to this lecture series. We are going to solve exercise for section 5.3 from the book Introduction to Real Analysis by Bartle and Sherbert. So in the previous video we solved question 9 to question 14. This is part 3 video, and in this we will solve question 15 to question 19. So let us start with the question number 15. So in question number 15 we are given the function fx equal to x square, and we are asked to examine which open intervals are mapped to open intervals, and respectively which closed intervals are mapped to closed intervals. So basically what we are asked is, if I is open, then for which I fi is also open. This is what we are asked. And if I is closed, for which I fi is also closed. So this is what we asked. So we have to examine for which i's this fi is open and fi is closed. Now, so since f is continuous on R, because fx is equal to x square is continuous function, being a polynomial function, so it maps closed interval onto closed interval. That is, if I is closed interval, then fi is also closed interval. But we don't know about open intervals, whether open intervals are mapped onto open intervals or not. So we will check for which open intervals this is true. Now observe that, let us look at the graph of the function fx equal to x square. So if you look at the graph of the function fx equal to x square, so it is similar to this. So this is your fx equal to x square, and as you can see, so if I take any interval in this here, if I take any open interval here, any open interval ab here, then the corresponding image, so this is your b and this is your a, so the corresponding image will also be an open interval, right? So this is your f of a, this is your f of b. So corresponding interval, this is also an open interval. But if I take any, if I take, okay, let it be this. Now if I take any interval around 0, then what is happening? Because 0 is the minimum point, so so now if I take any interval around 0 for the same function, so any interval around 0, so if I take a b equal to this b a, so this is our fp and this is say our a, this is our fb. But the interval is, if you see the interval, it is all these points are covered, all these points are covered. So it is basically the interval 0 to c. C is open where c is equal to maximum of whichever fa or fb. So this is the main idea. So we can see that if I take any open interval which does not contain the point 0, then that interval is open. The corresponding image of that interval under f is open. But if I take an interval around 0, then it comes out that it is not open, it is semi open, because 0 is attained at that, because 0 is equal to f of 0, so it is attained. So if interval contains 0, then it is not open. So let us consider, so let I be any open interval. So now we have two possibilities. Now we have two possibilities. Case 1, when 0 belongs to I, 0 belongs to I, then then f of I is the interval 0 to, okay, so we have to, because I is any open interval, so we have to take cases when I is finite open interval or I is closed. So sub case 1, I is bounded interval, that is I is equal to a to b for some a less than 0 less than b. So this is, then what will be our f of I? Then f of I will be equal to the open interval, sorry, the closed interval 0 to c, where c is equal to maximum of a square b square, fa fb, maximum of fa fb. Now case sub case 2, I is unbounded, so it either left side is approach minus infinity or right side or both, then clearly f of I will be the interval 0 to infinity, which is again not open, which is again not open. So in either case, if 0 belongs to I, then it is not open. If 0 belongs to the interval I, then it is definitely not open. So whether I is unbounded or I is bounded, so the interval is not open. Now case 2, when 0 does not belongs to I. So we have two possibilities, either I contains all negative real numbers or I contains all positive real numbers, and again in those two cases we will have either I is bounded or I is unbounded. So sub case 1, I is unbounded, then clearly f of I is of the form a square infinity, whether I is equal to minus infinity to minus a for a greater than 0, or you can say minus infinity to a or a to infinity. So whether I is of this form minus infinity to a or I is of the form a to infinity, its image will be a square to infinity, which is open, right? And now if I take, so sub case 2, I is bounded, so we, as that is I is equal to ab. Now we have two possibilities, so then either 0 is less than a less than b, or a is less than b less than 0. So in this case f of I will be, so in this case your f of I will be, because both are positive, so a square will be smaller than b square, so it will be a square to b square, or f of I will be from b square to a square. So in either case f of I is, so this implies f of I is open interval. So hence we see that from all the possible cases f of I is open interval if and only if I is an open, provided, not if and only if, because there may be some intervals which in fact it will come out to be if and only if, but let us not get into that. So provided I is an open interval and 0 does not belongs to I. So this is what we have done. So fi is an open interval if provided I is an open interval and 0 does not belongs to the interval I, then your fi is open interval. Otherwise if 0 belongs to the I, then it will be the interval which starts from 0 and it may go to infinity or at some point a. Now come to this next question number 16. So we have done question number 15. This completes our question number 15. So we are able to say we have seen that every the function f maps every closed interval to closed interval, because this is our theorem that every continuous image of a closed interval is a closed interval, but it maps an open interval to an open interval provided that open interval does not contain the point 0. Now let us move to the question number 16. So in question, let me just copy paste the question number 16. So it is of the similar type. In fact, now in this we are given two different functions. So this question can be done on the similar line. So I will just state the intervals which it will take to. So case solution, again it will map closed, both are continuous functions, both g and h are continuous functions. So g is a rational function, so it is continuous, and h is a polynomial function, so it is continuous, and domain of g is whole of r, again domain of h is whole of r, so they are continuous on r. So they map closed intervals onto closed intervals. So about closed intervals we are done. So we have to talk about the open interval. So let us first talk about the function g, which open intervals it maps to this gx. So if you see the minimum value of g, again like in the previous one, the minimum value of this function was 0. Similarly, if you look at this function g, so its minimum value is, again if so this is minimum when sorry, the maximum value is, it has the maximum value. So this function gx is a function, gx is basically a function from r to the interval 0 1. In fact 0 is not attained here, 0 so 0 to 1, right? So its range of, in fact we can write like this. So range of g is the open interval 0 1. So if x gets infinite, then it becomes open at 0 1, at open at that point at 0. Now but if you look at this 1 by x square, 1 by x square plus 1, now this is maximum when your denominator is minimum, and denominator is minimum when this is 0, because x square is always positive. So denominator is minimum when this is 0, so this is 0 when x is equal to 0. So again it will create, this will create problem at the point 0, and at all other points we will be able to get this result. So let I be any open interval, then case 1 0 belongs to I, 0 belongs to I, then sub case 1 I is finite. So I is finite, so it will take the case. So then I is finite, so that is I is oh sorry, I is bounded, not finite. I is bounded. So this implies that is I is equal to AB for some AB. That is I is equal to AB for some A less than 0 less than B. Then G of I is nothing but it is C to 1, because 0 is in this interval, so 1 is attained. G of 0 is equal to 1. So then C, where C is equal to, C is a minimum of, because it will take either 1 by, so it will take a minimum of 1 by a square plus 1 or 1 by b square plus 1, whichever is minimum. Then we have this 1 by a square plus 1, 1 by b square plus 1. sub case 2. So sub case 2, so now I is unbounded. So when I is unbounded, then this 1 by x square plus 1 will go to 0. So that means our gi will be equal to 0 is not attained at this. So it will be 0 to 1, which is not open. Again, this is not open. So when 0 belongs to I, then the interval gi is not open. The interval gi is not open. Now we will take the case when your 0 does not belongs to I. Case 2, 0 does not belongs to I. So again we have two subcases. Subcase 1, I is unbounded. So again we have two possibilities. If I is equal to minus infinity to a, where a is less than 0, then your gi will be equal to, so it will take all the values from 0 to 1 by a square plus 1, which is open. Again subcase, if I is equal to a to infinity, where a is greater than 0, then gi will be, again it will take value from 0 to 1 by a square plus 1, so which is open. Now if subcase 2, so if I is unbounded, then the interval we get is open. Now if I is bounded, so that is I is equal to AB. So now we have two possibilities, that because it can, both are negative or both are positive. So if 0 is less than A, less than B, then gi, what will be gi equal to? So it will be equal to, because as you increase the b, then your denominator, so as you increase your x, your denominator is increasing. So as your denominator is increasing, the number is decreasing. So it will become 1 by b square 1 to 1 by a square plus 1. Now if a is less than b, less than 0, then because when you are in the negative side, so the absolute value of a is increasing, that means a square is greater than b square. So again we will have this, so gi will be equal to 1 by a square plus 1 to 1 by b square plus 1, because the absolute value of a square is greater than b square, so this will be smaller. So we will have this interval. So again in this case, which is open, so hence from all the possible cases we conclude that, hence from all the possible cases we conclude that g of I is open provided I is an open interval with 0 not belonging to I. So if I is any open interval which does not contain 0, then it is open, then gi is open. So it gi maps open interval to open interval provided then that open interval does not contain the point 0. So we are done with g. Now we have another function h, so we have to talk about h. So we have already seen that h, because h being continuous, it maps closed interval to closed interval. So we need to talk about the open interval. Now we will talk about, to talk about the open interval, observe that. Now first you let observe that what is the function g, how the graph of function g. So it is like this. So this is the graph of hx equal to x cube for all x belonging to R. So if you take any interval, any open interval, then this will be again an open interval, because this is one function. so it does not repeat any value. So you will get for any open interval I, then the g of I will be an open interval, or h of I will be an open interval. You can easily prove it, because if you take I equal to ab, then h of I will be a cube b cube. If you take I to be in unbounded interval, which is minus infinity to a, then your hi will be minus infinity to a cube. If you take I equal to a to infinity, then your hi will be a cube to infinity, because h is an increasing function, so all the things will be preserved. So basically your h, you can simply write that I is open if hi is open if and only if I is open. I is open if and only if hi is open. So basically this is the proof. So we have seen that I is open if and only if hi is open. It is easy to see that for the function h, because it is injective and also it is increasing. It is one function, so it is hi will be open. I will be open implies hi will be open, because there is no repetition of the values. In all the previous cases we were saying that the function was repeating, coming back or going back, so that's why there was closed interval, but here there is no such case. So this completes our question number 15, sorry 16. Now we move to question number 17. So question number 17 is a little interesting. So in question number 17, we are given a continuous function that has only rational values, or we can take a continuous function that has only irrational values. We have to show that the function is constant. There is no other possibilities. So it's very simple. So given is f from 0 1 to r is continuous. Second, the f of the function 0 1 is contained in Q. That is, every image of this function f is a rational number. Claim f is constant function. So we will suppose. So we will take the contrapositive approach. So suppose on the contrary, f is not constant. That is, there exists x1 x2 belonging to 0 1, x1 not equal to x2, such that fx1 is not equal to fx2. So there exist 2 points at which the value of the function is different. That is why it is not a constant function. So since it is not constant, so there must exist at least 2 points at which the value of the function must differ. So we have got 2 points x1 x2 at which the value of the function is different. Now, so without loss of generality, we can assume that fx1 is less than fx2. Now, because these two numbers are different, and by density theorem we know that every between any two real numbers there are infinitely many real numbers. So by density theorem there exists k belonging to irrational number, k belonging to irrational number, some irrational, k belonging to Q complement, such that by density theorem this is possible. Between any two rationals there is irrational, and between any two irrational there is rational. So there exists an irrational number k such that f of x1 is less than k less than f of x2. Now by intermediate value theorem, because f is continuous on R, by intermediate value theorem there exists C belonging to R such that f of C is equal to K. So this implies K belongs to Q, since f of, sorry, this domain is our the set 0 1, so this belongs to 0 1. F of 0 1 is contained in Q, so this must belong to Q. because function takes only rational values. So k is a rational value, but here we are given that k is irrational, contradiction. Hence our assumption is wrong that f is not constant is wrong, thus f is a constant function. Similarly, if you would have taken similarly, because there are two questions asked in this, if f takes only irrational values, then again you will proceed with the same proof. So you will suppose that f is not constant, then you will be able to find two distinct points at which the value of the images are also different. Then instead of this k being irrational, then you will take, because these your fx1 and fx2 are irrational, so you will take a rational number between them. Then by intermediate value theorem you will get a point at which k is equal to fc. Now this being irrational and this being irrational will create a contradiction, and hence you will arrive at the conclusion that f is a constant function. So in either case f is a constant function, so we have to use intermediate value theorem in this. So this completes our question number 17. Now let us move to the question number 18. So now here the function f is given, f is not given to be continuous. It is not known that f is continuous function, but it has a property that for every x the function is bounded on some neighborhood of x. For every x the function is bounded on some neighborhood of x. We have to show that the function is bounded on I. Proof. So given is for each x belonging to I there exists delta x greater than 0 such that f is bounded on v delta x. So for every so that is f is bounded on neighborhood of each of its point in the domain. Then we have to show f is bounded on I. So we have to show this. So we will take the contrapositive approach. So we will assume that suppose f is not bounded on I. So assume that f is not bounded on I. So what does this imply? Because f is not bounded on I, so for each n belonging to n we will be able to find xn. There exists xn belonging to I such that mod fxn is greater than n. So for each xn we are able to find one point xn, because f is unbounded. So for each xn there will be some point x, for each n belonging to n there will be some point xn belonging to I such that f of xn is greater than n. So now xn is a sequence in I and I equal to ab is bounded. So this implies xn is a bounded sequence in I. So by Bolzano-Weierstrass theorem, by Bolzano-Weierstrass theorem, there exists a convergent subsequence xnk of xn converging to say x. So we have assumed that xnk is a convergence of sequence of xn that converges to x, that is your xnk converges to x. So now xnk converges to x, what does this imply? So xnk converges to x. Now what we will do is, so mark this as star. Now by hypothesis f is bounded in some neighborhood of x, that is there exists delta greater than 0 such that there exists delta greater than 0 and m greater than 0, m greater than 0 such that fx is less than m for all x belonging to v delta neighborhood of x, mark it as star. For for all, so let us call it as c because we are taking x here, so let us call it as c. X and k converges to c, make it c, then make this also c, so make this also c. So now because we have x and k is converging to c, and now at f is bounded at each of its points, so f is bounded in some neighborhood of c, so that is there exists delta greater than 0 and m greater than 0 such that fx is less than m for all x belonging to v delta neighborhood of c. So mark it as double star. Now what we will do is, because x and k converges to c, because x and k converges to c, since x and k converges to c, so for above delta, so instead of epsilon we are using this delta, so for above delta greater than 0 there exists m belonging to z positive small m such that x and k minus c is less than delta for all k greater than equal to m. For all k greater than equal to m, x and k minus c is less than delta for all k greater than equal to m. Now what we will do is, we will take m to be maximum of small m and capital M. So let p equal to maximum of capital M and small m. So p is maximum of capital M. So we take the natural number p belonging to n. Let p belongs to n be such that p is greater than equal to maximum of mm. So we are choosing a natural number such that p is greater than equal to maximum of m and m. Then now because we are taking this greater than equal to, because this m can be real number and we want it to be an integer, so that's why we are taking it greater than equal to a. Or we can say p is equal to your maximum of m and greatest integer function plus 1. So either we can take p equal to this, or simply we can write p equal to p is greater than equal to maximum of mm. So now we will work with the x and p. Now since p is greater than m, since p is greater than m, so this implies x and p minus c is less than delta, using this condition, the last condition that we have got, because for all k greater than equal to m, x and k minus c is less than delta. So p is greater than equal to m, so x and p minus c will be less than delta, and this implies your x and p belongs to v delta neighborhood of c, and this implies f of x and p is less than m using double star, or star, sorry, using double star. Now using double star, and from here what we have, okay, this mark it as a. So from a, because for each n belonging to n, there is f of x n is such that it is greater than n, so this f of x n p will be greater than np. So this implies, now from a we know that f of x and p is greater than np, and which is greater than p. This is greater than np and this is greater than p, so therefore we have p is less than m, because fx and p is less than m here, while fx and p is greater than p here. So this implies x and p is less than m, contradiction to the choice of P, because we have chosen P to be greater than equal to we have chosen P as maximum of M and M, but here we are getting P is smaller than capital M, so which is contradiction to the choice of P. Hence our assumption is wrong and f is a bounded function on I. So this completes the proof of question number 18. Now let us move to the question number 19. So it is similar to what we have done in question number 18. There is just so we have to give an example for this. So we have to give an example. So what it is asking is, let J be any open interval. G is a continuous function on J with the property that G is bounded on every neighborhood of this. G is bounded on every neighborhood. So it satisfies the same property except for the fact that this J is not closed. Here J, because this is closed, so by hypothesis f is bounded in some neighborhood of C. This C belongs to I. So clearly C belongs to I. This C we have used the we have not mentioned the use of closed interval AB, but notice that this C has to belong to I because it is bounded on every neighborhood of I, every point in I. So C must be a point in I. So C belongs to I because C is a limit point of I, and I is closed. So this is very important, we missed it. So this is very important because x and k is converging to C and x and k is a sequence in I. So this C belongs to I. So C is a limit point of I, and I being closed, it contains C. So now because C is in this interval I, so by hypothesis f is bounded on some neighborhood of C because this C belongs to I. That's why then only we can say that f is bounded on some neighborhood of C, because we are given in the hypothesis, we are given that for every x belonging to I, so that x should be in I. Here also if you look at this, the condition is same except for the fact that we have now we have taken the open interval AB. So then our C will not be in AB, so we will not be able to write the above proof. Now show by an example that J is not necessarily bounded on J, so we will take the function. So example we will take is, we will take J equal to the interval 0 1 and G from J to R as G of x equal to 1 by x for all x belonging to 0 1. Now this function is bounded at in every bounded in every neighborhood of x. So for let us show it that J is bounded for every neighborhood of x. Let C belong to J be any point. So we have to show that there exists some this. So then so now this is there. If you look at the number line, so on the number line, this is our 0, this is our C, this is our 1. So we have to find something which lies, which is, so we have to define some, we have to find some neighborhood and so that this is bounded. So what we will do, this distance is C minus 0. So distance is basically C. So we will take the delta neighborhood as delta equal to C by 2. So let delta equal to C by 2. Then for any x belonging to V delta of C, so this implies x minus C is less than delta, that implies x minus C is less than C by 2, and this implies your C by 2 is less than x less than 3C by 2. So this implies when you will reverse it, so 2 by C is greater than 1 by x is greater than 2 by 3C. So let k equal to 2 by C. Then for any x belonging to V delta of C, your fx is equal to 1 by x, which is equal to 1 by x, which is less than 2 by C, which is equal to m. So take this as m. So that implies F is bounded on V delta C of V delta C. Sorry, the function G. So this has to be G. So G is bounded on every point C belonging to. So since C belongs to 0, 1, so this implies G of G is bounded on V delta X for every X belonging to 0, 1. But clearly G is unbounded on 0, 1. We have already seen this. So hence the example. And this concludes our question number 19. So this completes your exercise 5.3. So let's end here. So thank you everyone. Have a nice day. Bye.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.